So what happens when you want to check to see if a sample is significantly different than what you expected? And so statistics really gets into now looking at what you observed and seeing if it's different than what you expected. So a lot of times you might have a benchmark, you might have a sales goal, you might have something that you're shooting for, and then when you collect all that data from all your salespeople, are you significantly different? And so to do that, we use what's called hypothesis testing. Hypothesis testing allows us to come up with a decision basically to see if something is different. So the word significant becomes really, really important. So I'm trying to keep this as simple as possible. I feel you do need to understand what hypothesis testing is. You may not see it again in something else, but what you probably will see if you have any exposure in your profession in the future to data and big data or just analytics in general, you'll probably see something called a p-value, and you should know what that is and how it what it does represent. And so one thing I'm going to say here, and as we get going, you'll see it, is that a p-value when it's less than 0.05 means the word significant. Okay, so 0.05 or less means significant, and you'll see why as we get going here. Now, of course, because it's statistics, we have to make it hard, right? We have to make sure that it's hard to follow. We have all these different rules and things like that. Let's kind of scrap that for now. And let's make this more about just understanding significant difference. And so when we look at that, what becomes important is what data do we have and what decisions can we make? Now, if you think about it in Chapter 7, in Chapter 8, we looked at it when sigma was known, and then we've also looked at it when sigma is not known in Chapter 8, and that's when we use the t-score. And then we also used z to come up with a confidence interval for a population proportion. And so we're going to do kind of the same thing, except we're going to do it for hypothesis testing. So still the same three types, and we're going to do the same pretty much thing that we did before. Now we're just doing it to compare it to a population mean or a target or a benchmark or whatever it is. To do that, to start with, we'll talk about null and alternate hypotheses. Really just that means what are your different decisions you can make? Is it significant or is it not? That's basically what we're looking at here. And so let's get into it. We'll do an example, and I'll break these up again into smaller videos for the last two examples. So when looking at hypothesis testing, again, it's nothing more than is something significantly different than what you were expecting. We always denote one component as the null hypothesis and one as the alternate. Now, when you did confidence intervals, you had tails. And if any value would be out in those tails, what that represents is the alternate hypothesis, which would mean that it's significantly different because it's so far away from the mean. If it's close to the mean, or relatively close, that represents your null hypothesis. And that's it. That's all we're looking at here. If it's a tail, it's the alternate. If it's the middle part or the mean, it represents the null in any case. And it's always that way for everything we do. So we can have basically three different types of tests, technically two if you look at it as one tail versus two tail. And what we can do is we can say, well, I want to know if my salespeople are significantly more than what I was expecting. And when you have a case like that, then it's looking at one tail, and it would be on the high side of your bell curve. Well, what if you want to know, you think your sales group did terrible, and you think they're significantly less than what you were expecting? Then you have a situation where it's on your bell curve, it would be in the smaller or the less side of your mean. And then what if you just don't care? You just want to know if it's different. Is it significantly different? Maybe you have 5 different regions, and one might be more, one might be less, and you want to compare each one of those individually to the benchmark of $1 million. And so you look at it, and one was at 980,000 on average. Well, is that good or bad? Is it significantly different than what you were expecting? That's what a two-tail test would be. So on here, if we're talking about significantly less, we're talking about this alternate here representing the tail on the left side of your bell curve. And if we're talking about significantly more, that's what it would represent. And significantly different would be either one, and that's what that would represent. So let me show you exactly what that looks like up here on the whiteboard. So if we're talking about significantly less, then what we're doing is we're putting that benchmark, and we'll just call it the population mean, right at the middle. And if that's $1 million, then that's $1 million. Did we do significantly less? Well, which side represents less? It's the left side. So that would be our alternate, which would be less than. That does not look very good. We'll do it down here. How about? That's less than. And then this area here represents equal to and greater than. The next one then what if we think our salespeople are fantastic and we think they were significantly higher than the mean, which again is represented right here. Then we're looking at the right side of the bell curve, and that would represent greater than here. And then this part down here would be less than or equal to. Again, the rest of this, so you can think of this middle area is always equal to, this is always less than, and that is always greater than. So then what about, we don't care which one, we just want to know if it's significantly different. Then what we're doing is a tail on this side, a tail on that side, and then obviously this represents less than, that is greater than, and this is equal to. And so actually what we say this is then does not equal to. So that would represent our alternate, as you see in the slide that you saw before, and then this would be the middle area. So this then represents both of these tails. So that's why it's called a two-tail test, a one-tail right tail or upper tail, and a one-tail left tail or lower tail test. And that's really all we're trying to do, is our mean. So then what we're going to do is we're going to find our mean, our sample mean, and if we find out it's way down here, guess what? Significantly different. If we find out it's right here, we're going to say it's not significantly different. It's close enough to the mean to say that they're relatively the same, and the only difference is based on randomness. If it's somewhere out here, and we do the test for the right tail, we say we're significantly greater than the mean. If we're somewhere down here, then what we can say is it's definitely not significantly greater than the mean. It's relatively close to the mean, and the difference is based on randomness. And then the same thing over here, whether it's here or here, it would be different. And if it's in the middle somewhere, it's just close enough to the mean to say that it's not significantly different. Notice I didn't say equal, because the values may not be equal, but they're not significantly different. And significantly different is important. Here's why it's important. Significantly different means there's something you can do about it. Randomness is randomness. You can't control randomness, but I can control something when it's significantly different. So if my salespeople are not different than what I was expecting, how am I going to change them? Well, I'd have to do something drastically different. Well, not to get them to that point because the difference is based on random. If they're down here, you know what? I might lose my job if I'm the manager, right? There has to be something. Maybe it's the management of it. Maybe it's an economic downturn, but there will be a reason why you're way down here. And that's why statistics can be so powerful in what we do. So with that, I feel like this one video becomes so important because we're talking about why we're doing this. And the why becomes so important for everything you do when you start looking at data. And you're gonna be looking at data because you want to see if there's differences. You want to see if what you expected is different than what actually occurred. And that's statistics at its best. And so with that, let's show you 3 different examples. One when sigma's known, one where it is unknown, and then one for population proportions. And then we'll call it a day when it comes to hypothesis testing. But in the end, I want you to understand p-value. And if it's less than 0.05, you're out here. If it's not less than 0.05, you're somewhere in here. Same thing down here. 0.05 means you're way out here. And you're greater than that, you're here. And then somewhere in here would be greater than 0.05. And then in the tails, you're 0.05. So let's see how that's done. I want you to use your ebook, and I want you to understand the problems, the how-to part. But of course, more important than anything is, why are we doing this? And so hopefully that helped out a little bit.